Hello everyone, my name is Yu Shiwei, and I'm a second-year PhD student from the Hong Kong University of Science and Technology, Guangzhou. Today, I'm honored to present our work. This work is a collaboration with Sen Zhang, Rong Kai-shi, Simon Feng, Pan Hui, and my supervisor, Professor Haining Liang. In this talk, I will introduce how we enable users to perceive virtual object weight during recasting interaction, using only visual feedback without additional haptic hardware. First, weight perception is an essential component for realistic interaction in virtual reality system. In the real world, weight affects how we move object, how much effort we apply, and how natural interaction feels. Many existing approaches attempt to reproduce this sensation using physical haptic devices, such as wrist mount force system or electronic muscle simulation. Where these methods can be effective, they are often costly, complex, and difficult to scale for everyday VR use, which limited their practical adoption. Because of this limitation, researchers have explored 3D haptic, which create a haptic illusion through visual manipulation rather than physical force. Techniques such as control display ratio modulation, tracking delay, and vertical offset have demonstrated that users can perceive weight differences purely from visual feedback. These approaches are attractive because they are low cost, scalable, and easy to integrate into existing systems. At the same time, VR interaction has evolved into two dominant paradigms: direct hand interaction and recasting. Recasting is widely used because it enables efficient interaction with distant objects, while reducing physical effort. However, managing weight in recasting is challenging. Unlike grasping or lifting, recasting lacks physical contact and motor cues, making it unclear how users should interpret a visual signal as weight. Furthermore, many 3D haptic techniques developed for virtual hand cannot be directly transferred because their interaction dynamics are fundamentally different. Meanwhile, this observation reveals several gaps. First, in previous continuous hand-object coupling used in previous 2D haptic may disturb users' experience and body ownership. Second, most studies focus on near-field interaction, leaving distant interaction underexplored. To overcome this problem, we propose the Reflex, a 3D haptic technique that introduce weight perception into recasting interaction. The key idea is to simulate weight through dynamic visual behaviors rather than modifying users' hands. Reflex combines visual displacement with dynamic ray deformation. The select object behavior as if it has inertia and resistance, where the ray visually bend on the load, creating an intuitive analog similar to the fishing rod under tension. Technically, Reflex models the object using a mass spring damper system. Instead of instantaneously snapping to the ray position, every object exhibits delay, motion, and vertical offset, mimicking inertia and gravity. At the same time, the ray visualization is redesigned using a Bézier curve, whose curvature changes dynamically according to the displacement. This deformation provides a continuous visual cue that reinforces perceived heaviness while maintaining stable interaction. Based on this design, we investigated two main research questions. First, why the Reflex enhances user perception difference in virtual object weights. Second, why the dynamic ray deformation improves user experience during interaction, or whether the additional visual complexity may influence users' judgment and interaction performance. To answer this question, we conduct a control user study using two alternative force choice tasks. Participants compare the weight of two virtually identical cups, one with a fixed reference weight and one with varying comparison weights. The participants have to lift the cup using the ray interaction and judge which one felt heavier. The participants complete the experiment. The study followed within subject design with 2 ray visualization and 10 object mass level. Importantly, both techniques use the same visual displacement mechanism based on the mass spring dampener model we designed in the reflex. The only difference between the two techniques was the ray visualization method. One used all dynamically deforming ray in reflex, while the baseline used a conventional straight ray. This design allows us to isolate the effect of ray deformation while keeping object dynamics consistent across conditions. The results show that participants achieved higher weight discrimination accuracy across all mass conditions. Object mass significantly affected performance, while revisualization did not change object accuracy. This indicates that displacement mechanism alone already convey weight information effectively. However, subjective results reveal important difference. Participants reported stronger perceived heaviness, higher satisfaction, strong presence, and lower workload when using reflex compared to the straight ray. Many participants noted that ray deformation provided immediate visual cues that made weight judgment faster and more intuitive. This suggests that dynamic ray deformation acts as a complementary signal that enhances perception rather than replacing displacement cues. After validating perception, we further evaluated reflex in an application scenario. We designed 2 VR tasks representing different interaction contexts. The first task we called Harvest Drop involved picking lightweight apples and placing them into a basket. The second task, Teddy Quest, required to move heavy objects such as furniture within a room. In both tasks, reflex was compared against conventional recasting methods. Participants completed a standardized questionnaire measuring different kinds of experience, such as workload, usability, user experience, and presence. Results show that reflex consistently increased the perceived workload compared to conventional recasting. However, participants often described this increased effort as natural and appropriate when interaction with heavy objects. Despite higher workload, reflex achieved significantly high usability score in lightweight tasks and substantially better user experience rating overall. Participants reported great enjoyment, engagement, and immersion. Presence score were also significantly higher across both tasks, and most participants preferred reflex over conventional recasting. From this finding, we derived 2 design implications. First, real object decouping allows designer to introduce rich pseudo-haptic effect without disturbing embodiment, because visual feedback can be modified independently from hand motion. Second, virtual weight should be carefully collaborated to balance realism and interaction efficiency, since excessive simulated weight may significantly increase workload and unnecessarily. In summary, we present reflex, a pseudo-haptic technique that enables weight perception in recasting-based VR interaction. By combining physical-inspired object dynamics with dynamic ray visualization, reflex conveys heaviness without specialized hardware. Across 2 user studies, the technique improved perceived realism, engagement, and presence while maintaining usability. These results demonstrate that meaningful physical sensation can emerge purely from carefully designed visual interaction dynamics. Thank you. This is all of my presentation.